Hello, everyone. Welcome to Skype a Scientist Live. My name is Sarah McAnulty. I run Skype a Scientist, and I'll be moderating the Q&A today. Ben, thank you so much for joining us. I'm so excited to hear about how our brains interact with games. This is going to be super fun.
No problem. Happy to help.
I feel like you look like you're in a podcast studio over there. You look so professional. It's really exciting. Okay, so everybody at home, Ben is going to say who he is, what he does, why he likes it, and then we're gonna give the floor kind of to you to ask questions. So if you have questions while we're talking, while we're going through questions, this is all about your curiosity. So submit your questions to the Q&A. You're welcome to put things in the chat, but if you have a question that you'd like me to read out loud to Ben, please do so in the Q&A so we can keep track of everything. Thanks so much for being with us today.
Yeah, no problem. And do interrupt me at any point as well. It's sometimes better to answer those questions as we go rather than wait at the end. So it's no problem. So hi, everyone. My name is Ben Dyson. I am a professor at the University of Alberta, which is a very chilly -10 this morning. We had a little drop of snow. And one of the things that I do at the university is that I do research into how people respond during competition. So the idea here is that we need to make decisions. Often we would like to win rather than to lose. And we can think about this in a variety of different contexts. So even something like politics, for example, might be an example of competitive decision-making, or even economics. So as we go through everyday life, we need to make decisions, and we need to make sure that we're doing the best that we can. But we know that inside the brain, there are mechanisms that essentially help us to figure out how well we're doing. And so what I do, some of my research is I look at the brain, and specifically we look at games as a sort of like a tiny little window of how competitive decision-making might work. So I'll be very happy to talk this. And one of the reasons why I really love doing this is because I also have an interest in game design as well. So it doesn't make me a better gamer, unfortunately, I will say, but we can't have everything, right? But I can go ahead and share my slides if you so wish.
Great.
All right. Yeah, so this is me. I'm also, you can, if you have any burning questions afterwards, I'm also on Twitter and email. And I just want to acknowledge as well that we've been on a long journey. So currently I'm at the University of Alberta. I used to work at Ryerson University and also the University of Sussex in the UK. So all of this work has been generated by being at these different kinds of places. So 3 take-home messages for you today, I hope. The first question that I hope to answer for you is, how can we measure brain activity? So that's the starting point. We want to know what the brain is doing when we're making decisions. The second question that I hope to answer for you is, how does my brain tell me how I win or lose? Or how does the brain let me know whether I'm doing good or whether I'm doing bad? And we know some things about this. And the third thing, that I'd like to answer for you is, well, what happens next? So say, for example, if I've lost or if I've won, does that put me in a particular mood or a particular state that might influence what I do next? So we can answer those questions in turn. So let's have a look at how we at all would be interested in the brain. Now, in one respect, the brain is a very boring thing to look at. So if you took your brain out of your head and you popped it on the table and you looked at it, it wouldn't do very much, right? It would just kind of sit there. Eventually, it would start to smell a little bit and things would start to ooze a little bit. And it wouldn't really tell you what it was doing just simply by looking at it physically. So in one respect, the brain is quite a boring thing to look at. But in another respect, it's probably the most amazing machine that we have. So within the brain, when you put it back into your head and connect it to your spinal cord and all those wonderful things, there's quite an amazing display of electrochemical activity. So within the brain, even though we can't necessarily feel it, right now you can think of all these sort of massive, tiny little connections that are going on within the brain. billions of cells talking to billions of other cells, exchanging electrical information and exchanging chemical information. So one thing that we can do is we can study some of those electrochemical exchanges, and we can look to see what happens in the brain without taking the brain out. So this is what I do, and specifically I look at the electricity generated by the brain. How might we do this? Well, we don't need to take the brain out. What we can do is we can put something on someone's head. This is kind of similar to a swimming cap that you might wear. And on that swimming cap would be tiny little electrodes, just like little ways of just listening in to what some of that brain is going to do. So we can show people information, and then using those electrodes on top of the head, we can try to figure out how the brain is responding to what we see, what we hear, and what we feel. So once we've presented information, we need to record what the brain is doing. And this is a very long word that I always get wrong. That's electroencephalography. It's basically the electrical record of what the brain is doing. So kind of like just squiggles. You can see here that there's just a bunch of squiggles that are produced that is trying to capture some electrical activity of the brain. Now, what we do in these experiments is we have to do this hundreds, if not thousands of times in order to average together the brain signal. So the brain is really noisy. So what we have to do is we have to try and get rid of the noise and try and improve the signal that we see when stimuli are presented. So when you do these kinds of experiments, people sit under these caps for maybe about an hour or so. So you have to be very patient doing these kinds of studies. So this is where we're at. Okay, so this is what we would use. So the brain, in order to examine the brain without taking the brain out, we can use tiny little sensors on the head, and that records some of our electrical activity. Now we can take that method and we can ask the burning question, how does this apply to games? So one thing that we will experience when we play games is that sometimes we are victorious and sometimes we are the loser. And we want to know how the brain is telling us this and what happens in the brain when we lose and when we win. So to do this, we examine simple games. So pick any game that might come to mind. That might be a sporting game, it might be a card game, a board game, a video game. It's often the case that there's an exchange between individuals. One person will lose and one person will win. So it's always the case in these kinds of games that we play that every time you play, you're either going to at least win or lose. And this is really important for us because we need to have people experience these wins and losses lots and lots of times. So remember that I said that when we're recording electrical activity, we need to examine this hundreds, if not thousands of times. Now, the game that we often play in the lab is rock, paper, scissors. Now, you might know this game in another way. It's also called stone, paper, scissors, Rochambeau. It's also called rock, paper, scissors, stone, which I don't quite understand, but there we go. And you might be interested to know that this game is really, really old. Rock, paper, scissors is a form of Japanese games where there are lots of different variations. So this is the Mushiken version of rock, paper, scissors, where you're competing, you're choosing a slug, a frog, or a snake, each with the little hand symbols again, but they have the same kind of interactions that you would be familiar with in rock, paper, scissors. So when we play the game, obviously there are 3 different outcomes in the game. Depending on what your opponent chooses, you can win, you can lose, or you can draw. And draws are really interesting, but I won't be talking about draws unless you ask me about them today. So you'll know rock, paper, scissors is a really quick, fast game. You win and lose really quick, and you can play it hundreds of times with the same individual. So what we can do is we can take that simple game and put it into our electrical recording method. So we would get people to play these games. They would be told whether they win or whether they lose. And what we would be looking for here is we're looking for a very specific part of electrical activity. Now, this has been studied for, I think, about 40 years now, and it's something called the FRN. We like to use lots of acronyms in science. This is called feedback-related negativity. We know it comes from a certain location on the top of the head, and when people have looked at where that electrical signal has been generated within the brain, there's another acronym for you that's called the ACC, this little bit here in blue. And what happens in the ACC is that there's a chemical that is received by the ACC called dopamine. And it seems to be the case that the release of dopamine controls the experience of win or loss. So if you lose, if you experience loss, that appears to reduce the amount of dopamine that is released. The ACC looks at the amount of dopamine, and then we can record that signal at the top of the head. So fairly complicated relationship between chemicals and electrical activity. But when we look, and this is data that we've collected in our lab, basically the take-home message here is that this is about 40 people's brain activity. And this is the time that it takes to register whether you've won or whether you've lost. So the win or the loss takes place, starts around here, and roughly around 250 milliseconds after you've been shown whether you've won or lost, the brain has registered that difference. So all you can, the difference here is between the solid line and any of the dotted lines, and you can see that the solid line is always higher than the dotted lines. So that's to say that when we look at this thing called FRN, losses are more negative than wins. So the important message here is that this is happening about a quarter of a second after you see the word win or loss. So this is probably before you yourself are aware that you've won or lost. So this is really cool, because what we can do is we can look at the brain activity that precedes kind of awareness of being successful or unsuccessful. So how does my brain tell me whether I've won or lost? So we think this relates to differences in a chemical called dopamine. There's an area of the brain that looks at the levels of dopamine within the brain, and we can record what that brain area is doing by recording an electrode from the scalp. So we know whether we've won or lost about a quarter of a second after winning or losing. The final question is, well, what happens next? So this is also really interesting for us, because we think that the experience of success or the experience of loss puts us in different kind of brain states. So you might be familiar with punishment and reinforcement. It's better just to talk about some everyday examples of this. So let's say, for example, that you might have been trained to stop picking your nose and eating it. All right. That's an example of lose shift. What's happening is that you're receiving negative feedback for your behavior, the picking of the nose and the eating it. And so you change your behavior, you shift your behavior. Alternatively, you might be rewarded for good behavior. This is known as win-stay. So every time you get a 10 out of 10 on a test or a gold star, you might be more inclined to do the same thing again, to study. So again, we can look at what people do following a win and following a loss in these kinds of games. And rock, paper, scissors is also interesting because there are two ways you can shift your behavior, right? You can sort of go from rock to paper, or you can go from rock to scissors. So the final thing that I want to tell you about today is something that we find really, really interesting. So if you were to play, let's say randomly, you would be playing each one of the three responses a third of the time. And this is kind of what you do after a win. So once you've won, that doesn't necessarily mean that you stay with the same response. That kind of makes you more unpredictable. And so it makes it harder for your opponent to beat you. What we see after losing, though, is you're much more likely to change your response. And unfortunately, this makes you much more predictable to your opponent. So this tells us a little something about the brain states that we might find ourselves in. Once we've lost, we might be making worse decisions in the future, which unfortunately would increase the chances of losing again, which unfortunately increases the chances of making bad decisions in the future. So losing can make these cycles of behavior happen where we repeatedly do the wrong and the bad thing. Winning makes us in a much more confident, in a much more optimal cognitive state. So why would we be interested in lose shift? Well, if you think about it, sometimes it's much more important to change your behavior if you are going to be losing. What I want to say is that here the zebra fears a loss and is changing their behavior. That would seem to be a much more important mechanism than staying with your behavior if you're winning. So this is why lose shift might be more important than win stay. So we know that losses might put us in a much more vulnerable state than winning. And this is where we want to go next, because we all need to fail. We all need to experience not doing so well. That's true in education. It's true in my life as well. But that's how learning happens. So what we're doing in the lab at the moment is trying to figure out how we might overcome some of those negative reactions to failure. All right, thanks a lot. And I'm very happy to take questions.
All right, that was super cool. Let's get into some questions. Here's a question from an anonymous attendee. Some parents will say that games rot our brains. Is that true?
Well, it would. There's lots of different games out there, and there are lots of games that have been studied with respect to improving your cognitive abilities. So I'm not wedded to any of these particular ones themselves, but things like Lumosity, for example, which I think was quite popular maybe 3 or 4 years ago, that was a series of games that were actually based on cognitive tests. So it kind of depends how you're engaging with the games. So it's pretty, there's lots of pushback against things like loot crates, for example, in games, those things that you have to pay for to be better. But there's quite a bit of evidence to suggest that that kind of cognitive engagement that you have, thinking about what your opponent's doing, those kinds of things might just help you in terms of maintaining that kind of brain training and that cognitive training. At least that's my hope when I play a game, is that I'm sort of exercising my cognitive muscles.
Sounds good. All right, the next question is from Garden Spot Middle School. While you're using the electroencephalograph
Correct.
cap,
Gold star.
Thank you so much. What does it look like if you're reading, for example, or doing something else?
Right. So the kind of cool thing about EEG is, so if you're reading, what will be happening is you will be moving your eyes a lot. Okay. And one of the things about recording electrical activity is that it also records muscles. So muscles generate electrical activity. And one of the most powerful muscles in the head is the eye. So when you're moving around and you're reading, you'll see all these kind of very, very large, this large electrical activity that has nothing to do with the brain at all. So often what we do is when we record this EEG is we have to sort of filter out what the eyes are doing, because the eyes, essentially the electrical activity generated by eye muscles, essentially contaminates or interferes with the brain activity we want to see. If we're looking at like the top of the head here, no muscle there at all. So the signal can be sort of nice and clean. So yeah, so when you're reading, we know if people are reading because we see those eye movements on the EEG. Same too if you grit your teeth. If we know that a participant is getting annoyed or tired, you can see all this very, very sort of scratchy EEG as well. So that means we should go in and just make sure they're okay.
Sounds good. The next question is, how do the small sensors on the cap collect brain activity?
Yeah, so what we have here is we have, they're called electrodes. So kind of similar to if you were, have your heart rate measured or something like that. I know you can do that over phones and things, but you would put a tiny little bit of gel, conductive gel. And what that gel tries to do is it tries to conduct any really tiny electrical activity. So thinking about it, the brain is producing all these chemicals and electrical activity, but what that electrical activity has to do is it has to pass through the skull, which is really thick, right? So we're only going to get some of that information. So you can't feel anything on your head. You can't, you don't get an electric shock when you touch your skull or anything. So these sensors have to be really precise and really sensitive. So this is why recording it is really noisy. So it's only a small portion of the electrical activity that we get from the brain. But if we use really sensitive electrical sensors, they're looking for that electricity. And hopefully we get some of it, not all of it.
Sounds good. All right, our next question is from Ms. McNew's third grade class. If you lose a game, is it hard to release negative feelings?
So this is what we're working on in the lab. So that seems to be what we would call an individual difference. Some people are like, I'm just playing for the fun. Doesn't matter. I win or lose. I'm just here for the game. Some people are really competitive. I myself have learned to be the first one because I lose too much. So I'm like, I'm going to lose here. So I should just enjoy the game. But one thing that we're doing in the lab at the moment, actually, so the idea is that we would try and sort of normalize those experiences to failure. Okay, it's okay. You are going to lose at some point. You are going to fail at some point. So in the lab, what we're doing is we're getting people to play games, but we're getting them to play the games as badly as possible rather than as well as possible. So there's some interesting data that we're getting to suggest that when you're intentionally trying to be as bad as possible, the strategies that you show in terms of what we would say getting as many losses as possible rather than as many wins as possible, you're actually as good at doing that as you are when you're trying to win. So there might not be necessarily anything inherently bad about failure. It might just be your reaction to it. And if we can sort of try to minimize or normalize those reactions, that might be a really good thing for education.
Cool, thanks. The next question is from Mrs. Lindquist's fifth graders. When you're collecting data and doing these tests, what types of games do you have people play the most?
So what we do, because we want to try and get as many signals as possible, is we try to get people to play simple games. So things like, I don't know if you've ever, so rock, paper, scissors is one example. There's also a game called Matching Pennies, which is really, really simple. You take 2 pennies, and if your opponent pick a side, if you match the pennies, you win. If you mismatch the sides of the penny, your opponent wins. And you can play that hundreds and hundreds of times to see who is the better player. We've also started designing games in the lab that will do specific kinds of things for us as well. So It's not the case that we would take something like Minecraft, for example, or Witcher, or one of these massive games, because it's going to be very, very difficult for us to figure out exactly what's happening in the game and to control everything. So with simple games, we can control them very easily, and we can also get people to play rapidly as well. So those are the kinds of games that we tend to use in the lab.
Super cool. Melissa wants to know, what inspired you to get into this field?
Hi, Melissa. So it was a complete accident. So I'll tell you a story. We had a lab meeting one day, and we had some students in the lab. And usually what we would do is I would ask each individual to see how they were getting on, like a progress report, which everyone dreaded. And no one wanted to go first that day. And so the students played a game of rock, paper, scissors to decide who would go first. And then we spent the rest of the lab meeting talking about the decision-making processes that they went into to decide what they thought their opponent was going to do. And we found this absolutely fascinating. And then we ended up doing research on it. And then we ended up actually writing it, that those students actually, we got a published paper. They were involved in that particular study. So that's actually where it started from, just a very simple kind of observation. And we just went from there.
Very cool. Awesome. Our next question is from Jonathan from PSIS 109 in Brooklyn. How much control does the average person exert over their own body and emotions? So if you're a sore loser, are you stuck with being a sore loser forever, or can you change that in yourself over time?
All right. Hi, Jonathan. So so there are things that we call sensitization and habituation. So depending on the kind of response that you're getting, sometimes you might be less sensitive to it, and sometimes you might become more sensitive to it. So, you think about something like a fire alarm. All right. So immediately that's like very alerting and arousing. But, if you have to sort of, calmly walk out of the school or whatever, and it takes you 3 minutes to do so, then by the end of it, you've sort of become habituated to the sound, right? So it's not necessarily the case that there is a one-to-one relationship between winning or losing and your reaction to it. We think that those reactions might change as a function of the amount of time that you win or lose. So something that's kind of interesting is that when a loss is rare, you really pay more attention to it. So if you're really good at something and then you kind of lose, and it's like, well, that's weird, I kind of lost. Like, I wonder what happened there. So that kind of experience you might be more detached from that, and you might learn more from it because it's a rare event. So sometimes it depends how frequent or rare those events are. And it also just depends what's going on the day too.
Very cool. Our next question is from Mrs. Leftwich's 8th grade class. Do people react differently when they think more luck is involved in a game?
Yeah, that's a great question. So we're actually studying that as well. And I'll let you into a little secret in that sometimes when we run our studies, the computer cheats, right? So we design a computerized opponent. And what the computerized opponent might do is it might look to see how the participant has responded and then change its response so that it will win. So this is a way of sort of guaranteeing that everyone will win or everyone will lose. And we think, so in those cases, that's kind of pure luck, right? There's nothing that you can do to control the situation. Or something like a lottery, there's nothing that you can do to control the situation. And we do think that those skill-based games or those luck-based games have different reactions in the brain. Not at this FRN level, but if we look a little bit further on in what the brain is doing, there's another component that would kind of come on when we need to kind of update our model about what's happening. So it's like, oh, that's sort of strange. I need to change what I'm doing. So that kind of lose shift behavior, for example, might come on in a strategy game, but it doesn't necessarily come on in a random game, because we know that there's really nothing involved there. But that's a really great question, because sometimes we tell our participants that this game is random and they don't believe us. They insist that there's a strategy somewhere in the game and that they can beat the computer. And when we've told them that they can't. So even if you were playing a random game, sometimes you won't believe us anyway.
Interesting. All right. The next question is, what else do people use EEGs for?
Yeah. So you can use EEG to record the brain's response to sound, response to pictures, to language, to your own motor control. Really a cool observation from the motor literature is that if you were all just to sort of decide when to raise your finger, right? Like just do that. When you record brain activity, it looks like that there is brain activity prior to your decision to raise your finger, which is kind of weird, because you would think, kind of almost suggests that your brain is in control of you and you don't decide what you have the illusion of deciding when you're going to raise your finger. But actually, if you look in the brain, there's a signal before you indicate that you've decided to raise your finger. So lots of really cool stuff that you can do with EEG. The beauty of EEG is that you record it with millisecond precision. So like 1,000 milliseconds in a second. So you can really see really early on what the brain is doing.
Very cool. The next question is from Karen. Can you say more about how the lose shift behavior creates cycles of behavior?
Absolutely. Hi, Karen. Yeah. So let's just go here. And so what we have, if you were to play any response equally, that would be, you would play it 1/3 of the time. So when you experience a loss, you're less likely to pick the item that you just picked, and you're more likely to shift to 2 of the other items. So the problem is that your opponent may well know that. So that increases the opportunity for your opponent to pick something that's going to beat you in the future. So this is where the cycle of sort of bad decision making comes in. Unless you play at 33 1/3, all of the other responses, it's like a tell in poker, right? You're more predictable in what you're going to do. And if you have a savvy opponent, that opponent is going to take advantage of that and increase the likelihood that you're going to lose again, which increases the likelihood of you shifting your response, which increases the likelihood of your savvy opponent picking the item that's going to beat you. And so that's where these cycles of suboptimal decision-making come in. And you can kind of see how this is really important for something like gambling behavior. So someone who's losing a lot is more likely to make worse decisions, which can have obviously fairly catastrophic financial implications too.
Yeah, absolutely. Very interesting. All right, the next question is from Trenton. This is a cool question. So how do you, I don't know if this experiment has happened yet, but have you looked at what the brain result is when you are working on a team? So in like a co-op game where multiple people are trying to win together as opposed to one person by themselves?
Yeah, so one thing that we don't do, but other folks are trying to do at the moment, is to record brain activity simultaneously in 2 people when they are cooperating versus whether they are competing versus collaborating. So you can, in addition to looking at these signals related to win or loss, you can also look at things like what we would call, I think, coherence and the kind of correlation that one brain has to another. So it is almost seeing, are your brains remotely in sync with one another? Are the oscillations, are the rhythms of the brain similar when you're cooperating successfully? And are they kind of out of sync when you're unsuccessfully cooperating? So you can definitely do those kinds of experiments. They're pretty involved, and we don't do those experiments just yet, but that's a great question.
Sounds complicated. As a person who's had to analyze data before, that sounds like a real pain in the butt to try to figure out, but very cool. The next question is from Garden Spot Middle School again. What if a person was mad or angry while wearing the cap? Like, can you look at the readings on the EEG and say this person is happy, this person is sad, or is it just too hard to tell?
Yeah, so we can't tell whether someone is happy or sad while they're wearing the cap. Obviously, if someone is unhappy wearing the cap, they can just take it off and stop doing the experiment. So that's one thing that we obviously allow people to do. So at the moment, the way in which we decode this activity at the time it's being recorded is in a rather crude way. So we would look to see if someone's moving their eyes. We could tell if someone was sleepy. So if you're falling asleep, the brain starts to generate something called alpha waves. So these kind of large scale, kind of slow wave activity that would indicate to us that the participant is feeling sleepy. So that's about as far as we, after the fact, and we analyze the data in a complex way, we might be able to figure out some other things. But at the time it's being recorded, we would know whether they were sort of gritting their teeth, moving their eyes, feeling sleepy, but that's about it.
Sounds good. Rebecca wants to know, how long have you personally been studying the brain?
Hi, Rebecca. Yeah, so I started studying the brain in 2001. So I got trained in this technique over in Toronto, and I've been using it ever since. So the technology has really advanced in 20 years. So, you know, if you think of it almost like pre-internet, post-internet days. So now you can record brain activity really simply. You can just sort of have a portable device. So usually you would have to come into the lab, sit in a chair and be hooked up to everything. Now you can just put everything in a backpack and go skating.
Sweet. Very cool. An anonymous attendee wants to know, do you play video games? And if so, which are your favorites?
I more play board games than video games, I guess. My favorite video, oh my goodness, I would have to say it's not for I would say Dead Space 2 is probably one of my favorites because of the atmosphere of the game. It's very scary. And I've also really enjoyed playing Subnautica recently. It's a game of underwater exploration, and again, because of the environment that it creates, I really like the sort of immersion that those kinds of games give you.
It's very cool.
And I should also mention that I'm also terrible at Hearthstone, even though I really enjoy playing it.
Sounds good. That's one I have not heard of yet. Very cool. All right. So another question: what age are the research participants that you're studying? Our grade 8 students want to know.
Yeah. So usually we set a minimum at around about 18. So often we test university students. So that would be around that age. But I also collaborate with other individuals who record the brain activity of older adults too. So these are individuals who are in between about 65 and 80. So we can compare the brain's response to these kinds of things across the lifespan too, which is super interesting. So question is, do older adults experience wins or losses, or is their cognitive system the same or different from an individual who's just developing those kinds of cognitive systems and skills? And there are some interesting differences between the way older adults and younger adults respond to things like incentive, for example. So, you know, you're going to get 3 cents if you do this right. You're going to have 3 cents taken away if you get this wrong. That changes as a result of age.
Very cool. Our next question is from ETN. Do you like your job, and what is your favorite part of your job?
Yeah, so really like my job. It's really nice to do something that I feel passionate about, that I'm interested in. I think that's the kind of key to a happy work life is really to find an interest, explore as much as you can, get into those things that doesn't feel like work. It kind of feels like fun, or you don't notice where the time goes when you're reading about something or looking at something. Those are the kinds of things I think that really make the job satisfying. And I would say that that's the funnest part of the job. I've also actually really enjoyed teaching. I really enjoy teaching too. And remote teaching has been a challenge, but I think we found some ways to make it interesting and fun too. So that's also been a challenge, but also a fun one.
Yeah, awesome. Thank you. All right. One last question from the audience, and then we're going to ask the same two questions that we ask everybody at the end of every session. All right. Okay. So the last audience, have you studied the reactions of bystanders, like sports fans? How do brains react to a team or player winning or losing?
Hey, yes, we have. And in fact, this is exactly on this slide. So what we've done is we've looked at the brain response to when you're playing, and looked at the brain response to when you're observing someone play. And at least at this stage, you get exactly the same reaction. All right. So you can see that the solid line is higher than the dotted line, both in the blue, that's when you play, and both in the orange, that's when you observe. So at one level, you know when someone else has won and lost to the same degree that you yourself has won or lost. But what I'm not showing on this particular graph is that there are then differences in how we might update our information. So observation is a little bit more distant. So that has fewer implications for how we change our behavior in the future for when we're actually playing. But I really appreciate that question, because depending on your relationship, I think, with the individual or team who is winning or losing, you might get a very, very strong reaction, right?
Yeah, for sure. All right, very cool. All right, we ask everybody the same two questions at the end of every session. The first is, if you had everyone's attention in the whole world and you could tell them one thing about your area of expertise, what would it be?
Don't worry about failing. It's natural and everyone does it.
That's a great answer. Great answer. Next, you still have everybody's attention in the whole world, and you can tell them one thing about literally anything. It can be as big picture important or small and important to you. Whatever you'd like. What do you tell them?
I would say that as you're going about your daily business, find the things that interest you. Find those things that don't feel like work, and it just makes it much easier to enjoy yourself and increases the chances of success. You're already invested in the thing that you find interesting, so pursue that goal. That's right. Somebody in the past once said, whatever you are, be a good one. So that really can lead to that. Okay, wonderful. Yeah. Thank you so much. Everybody at home, our next session will be on April 18th. We're going to be talking about ancient tools. So it's going to be like an archaeology, anthropology themed session. So I hope to see you all for that. Is there anything else that you'd like to share, plug, send people to, Ben? No, if you have any more questions, you know where to find me, and I'm very happy to answer them for you. Awesome. Well, thank you so much for taking the time to teach us all so much today and then talk with us. This was really, really interesting. Absolutely. It's been a pleasure. And thank you for hosting. It's really, really great. Skype a Scientist is really, really great. Love it. Thanks. I really appreciate it. Okay, everybody, we'll see you next week. Kay, thank you for interpreting, and we'll see you next time. Bye, everyone.